Hey everyone, welcome back, and today let's solve Leetcode problem 3228, titled Maximum Number of Operations to Move Ones to the End. Right, so kind of to summarize the problem statement here, effectively we're given a binary string S, and we can repeatedly pick any adjacent kind of 10 strings or 10 strings and slide that one right over all the zeros until it hits another one or the end, right, of the string, that is. And we have to return the maximum number of such operations that we can make. So, effectively just kind of glossing over the examples as well. In example 1, the maximum number of operations we can make is 4, hence the reason why our output is 4. We can first just choose index I0 and drag that across to be 0, 0, 1, 1, 1, 0, 1, because this one would go all the way here after being dragged across these two zeros until it hits this one, and we keep doing that until we can't do that anymore. And notice how we can't ever do that when all the ones are all on the right side of the array and all these zeros are on the left, because once we have all the ones concentrated to the right, there are no zeros for them to go across, and so there are no operations that we can make, and so that's why that's our kind of stopping point, if you will. Applying the same logic to example 2, notice how all the ones are already at the very right of the input string S, and so we can't actually make any operations, and so this is simply an output of 0 as the maximum number of operations we can make. So the length of our input string S is rather large, between 1 and 10 to the 5th power, right? That kind of tells us that we can't have too slow of a solution, otherwise we would get a TLE, and that also kind of tells us, okay, we can worst case have a linear runtime complexity, because anything like big O of n squared or anything worse would give us a TLE, right? Because this is between 1 and 10 to the 5th power as our bottleneck, right? And as set index I, kind of just confirming what the problem statement is essentially going to be binary. We're either always going to be dealing with either a 0 or a 1 in our input string S. So how are we really doing this? Again, the goal is really just to count the number of, or rather maximum number of valid operations without actually simulating every slide, because that would just be way too slow, and we'd get a definite TLE if we simulated every slide possible to calculate that maximum value. And so we have to really make that key kind of observation that this is really like a greedy or counting type of problem, because as we really scan from left to right in our input array, or rather our input string, we're going to keep track of how many ones we've seen so far. And once we actually reach a 0, that would be the last 0 in a block before either a 1 or the end of the string. That would be like the 0 that's immediately followed by the 1, or it's the last character, or each previously seen 1 can be moved past that 0 block once, and that would contribute 1's operations, or the number of 1's operations for that 0 block's end 0 positions, right? So effectively every time we actually counter like a terminating 0, we can simply just add the number of 1's to our answer, and that kind of ties back to the main observation that we can make, is that we don't actually need to know the block lengths explicitly. We only really need to know where the 0 blocks end relative to the future ones, that is, right? And the reason why this actually works is really because each previously seen 1 we can really pair with a 0 block, because it can really slide over at least once, right? And if we just count at each 0 block the boundary, that would accumulate the maximum points without any like messy simulation type solutions. And another problem, or rather another observation that we can make, is that scanning once and counting the seen ones is more than enough, right? That would mean it'd give us a big O of n runtime complexity and a constant extra space complexity, which is really what we need to avoid a TLE and obtain a efficient solution for this problem and its corresponding input constraints. So let's go ahead and get into the solution here. And the first thing that I'm going to do is, of course, initialize my answer. So let me just exceed the size of this. Initialize my answer to be 0. And like the name suggests of this variable, the whole point of this answer is simply just to hold the total maximum number of operations that we can perform. And of course, it's going to start at 0. Effectively, this is what we're going to return at the end. After we populate or update it, we'll be returning the answer. Now, once we do this, we're now going to get the total number of 1's that we've seen, and I'm going to call that 1's. And of course, that's also going to be initialized to 0. The whole point of this is to simply just track how many 1 characters that we've encountered so far as we iterate from left to right in our input string S. Once we get that 1's out of the way, I will now actually initialize, or rather just store the length of my input string S in a variable called n. And I really just usually do this for best practice, and because it really just helps me simplify the amount of typing that I have to do my solution. Whenever I'm dealing with any data structures, I'll always like to store the length of that data structure input in a variable called n, and so that's basically just the length of the number of characters in my input string S, really just that we can reference the neighbors really quickly and easily check for the last index without having to actually type out length of S each time that we're trying to access that value, right? And it's simply just the string length. Now, once we get that out of the way, now we can actually begin iterating over our input string s using a for loop from left to right, and so I'm going to do that very thing. And so instead of typing for I in the range of length of s, I can only just type for I in the range of n. Another reason why that n is very handy, because we don't have to keep using length of s every time we want to access that, right? So we're going to start a for loop to scan each index I from 0 to n minus 1. Effectively, we're just going to iterate through each character position, and at each step, we're simply just going to decide whether to update ones or whether to add to our answer. Now, the first thing that we're going to check for each index is the current index actually a 1? Meaning, is it the actual string 1? If it is, then quite intuitively, we're going to increment the number of ones that we've seen by 1. The reason why is because we've seen one character. And so we're going to increment the count of the ones, or the variable ones, by 1. Right? Because, of course, we've seen it one more time. We have to increase the count of the previously seen ones, right? And that's basically just going to contribute like the later moves. Now, once we do that, we're in the else conditional, meaning what if the current character is not a 1? That would mean that the current character is 0. And so if that's the case, we have to then check whether the 0 is the last 0 before a 1 or the end of the string. And the way we can test that is simply just if I is equal to the end of the string, or n minus 1, or the next character after this I, meaning s at I plus 1, is a 1, meaning it's equal to 1. And so else, if that's the case, if I is the end of the string, meaning it's equal to the last index, or n minus 1, or s at I plus 1, the next index after I, is equal to the string 1, that means that 1 is right after this current 0, then either way, we're going to increment to our answer the number of ones that we've seen so far. Why is this? Well, because when this 0 is followed by a 1, or it's the final character of our input string s, that would represent the terminating 0 for a 0 block, right? Each previously seen 1 can perform one operation that's associated with this termination, and so we simply just add the number of ones that we've seen so far to our answer accordingly. Now, once we actually compute that, at the end of this for loop here, once we iterate through all the indices n with this same logic here, based on if it's a 1 or a 0, and if it's a terminating 0, we simply just return our answer at the end of this solution outside of the for loop once it actually is done executing, or in other words, once it terminates. So unless I made any syntax errors here, they should be accepted and they should be a valid solution. So let's go ahead and verify that. And as you can see, this really is just about as efficient as you can get it to be. So, on a high level, again, how are we really solving this problem? Effectively, we're really just iterating through, as we usually do, the string from left to right exactly once with a singular for loop here for that efficient runtime complexity. And we're maintaining a running count, basically just ones, of all 1 characters that we've seen so far in the input string s. And every time we actually encounter a 0, that would mark the end of a 0 block, meaning the next character would be a 1, or it's the last character in the string. And so if that's the case, every time we encounter a 0 block, or rather a 0 that marks the end of a 0 block, we then add the number of ones that we've seen so far to the answer. And summing all the ones at those termination points would simply just tell us how many 1 characters can be moved over zeros in total, and that would equal the maximum number of allowed slide operations without actually explicitly simulating each slide in a more efficient manner. Again, main observation, the algorithm really just leverages linear scanning and our greedy counting kind of methods here to avoid very costly per move simulations where we have to simulate every single different slide manually, and then we'd have a very slow runtime complexity, right? Which brings us to our complexities. And although we talked about this pretty briefly in our explanation and our recap, just to kind of go through this again, the runtime complexity is very straightforward, very intuitively just big O of n, or linear, or n is the length of our input. And the reason why is because we really just do a single pass over the string, and each index is processed in big O of 1 or constant time. This really is just a one-pass singular for loop solution. We're iterating through each index exactly once in the input string s. Right? And for our memory or space complexity, it's actually going to be a big O of 1 or constant. And the reason why is because besides this input string s that we're already given with, we're not actually using any extra auxiliary memory or any extra data structures. We're only using a few integers like answer, ones, and n, which don't scale linearly with our input. And so because of those, just a few extra integer variables, we're really just going to have a big O of 1 or constant memory complexity or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye. Oops.